ओके, अस्सलाम वालेकुम। चलें स्टार्ट करते हैं। लास्ट टाइम वी वी वर एट occupancy number, and for occupancy number, that is the occupancy of a state, of an eigenstate with particles. So we developed two operators. One is the annihilation operator, and the other one is the creation operator. Both these operators are non-Hermitian operators, as AI dagger is not equals to AI. I is the ith state. Yeah. And so since they are not Hermitian, so their linear combination can be made Hermitian by an appropriate choice of a conjugate. Yeah. So in fact, in this particular case, we developed two non-Hermitian operators, AI and AI dagger, and we also relate them to the change of basis. And so now what we did last time was the change of basis. So just to recap, uh, so we have those two operators, that is the annihilation and creation operators. Uh, Annihilation operator, uh, which was AI, and creation operator, which is AI dagger. AI and AI dagger are not Hermitian. The change of basis, the change of basis that we did was for AI dagger, we wrote it as summation over Q B Q dagger, and then we have the LQ KI, this which is the overlap of the KI original or previous basis to the new basis LQ. And similarly, we have this AI, which is summation over Q, and we wrote it as KI LQ as BQ. So since AI and AI dagger are conjugate to each other, so you could see the order of appearance of these operators when you are doing the change of basis. So we have change of, in case of AI dagger, we have BQ dagger times the overlap between the previous basis and then the new basis. And in case of BQ, which is conjugate to AI dagger, we have first the change of, so we have the first the previous basis and then the new basis, the overlap between the new and the previous basis, and then we have this operator, which is in fact the annihilation operator. So these operator uh, this is basically the change of basis from the old basis and to the new basis. And with it, we have also the uh, change of basis from the new to from the old to new. We also change the operators. Yeah. Okay, so now we start operator algebra, which is very important because then we would, in this particular article, we would develop the commutation relations and anti-commutation relations. So, what are the commutation relations for what type of particles commutation relations deal, and what type of particles the anti-commutation relations deal? That is basically the main idea of this article, that is operator algebra. So we start with operator algebra, and we are doing operator algebra for creation and annihilation Operator. So uh, if we create one particle, that is, if we create one ith particle and one jth particle, then the order in which it is done should be important. That is, how you create those particle. What is the sequence of creation of those particles? And the only difference that is if they are, if you are saying that what sort of order you are taking, that is creating one ith particle and one jth particle. So if you create one ith particle first and then one jth particle second, then and if you change the sequence, that if you create one jth particle first and then one ith particle, then in these two creations, that is creation of ith particle and then jth particle, or creation of jth particle and then ith particle, the difference between these two creations of two particles, the only difference would be in some sort of a phase factor, and that phase factor we can denote it by some symbol, let's say lambda. So the difference in creating particles, first particle, second particle, third particle, fourth particle in any sequence or order is different from any other sequence or order by a factor which is known as a phase factor. So let's emphasize on this and then try to develop the commutation relation. So if we create one ith particle and then one jth particle, the the order in which these two particles are created is not important. The only difference is a phase factor. And let's say we call it as lambda. And so uh, these two, these should be same, except for lambda. And when they are same, so we can say that AI dagger, AJ dagger. So first you create the jth particle for from the state psi, for the state psi, which is equal to AJ dagger, AI dagger of that state. So they are equal. The only difference is some factor which come as a prefix, which is in fact your phase factor. So for any initial state psi, so this is true for any initial state psi. So you start with creation of those two particles, first creating jth particle and then creating ith particle, or you create first ith particle and then jth particle. These two creations of two particles is same. The only difference is basically this factor जो यहाँ पर appear हो रहा है, which is the lambda factor. That is, there would be a change of phase of that particular state जिसके अंदर दो particles you have created. Yeah. If the equation is transformed, now you need to think about the change of basis. So if you change the basis, representation. That is, if you change the basis representation from the eighth representation to the bth representation, then you have to use those change of basis representation relations जो अभी हमने ऊपर लिखी हैं. So if the the equation is transformed to the bth b representation or the bth representation, then your equation would become, so we could think about the this above equation. ये equation है, इसको we can write it as a sort of ai dagger, aj dagger, minus aj dagger, ai dagger of psi, which is equals to 0. Yeah. And then one could think about the change of basis. So the change of basis for both these, in fact, AI dagger and AA dagger using these two relations. So using these two relations, we can substitute the values of AI dagger and AI in this equation. And what we get here, we get, so after substitution, we would get summation over k comma l. So we have these two, in fact, uh, bases, represented bases. So lk ai. Remember, this is coming from here, and then we have ll k. Let's say kj. This is coming from this one. Yeah. Then we have, and also for this. So I just ये करें बीच में minus sign. Then we write for the other one, that is we write for the jth, so that would be uh, L L K J, and then we have the first one L K and K I, and this whole, and we have psi here equals to 0. Yeah, sorry, we need to write uh, we need to write the change of basis. We need to also write the basis. So this is wrong. Remember, इधर ये बी क्यू डैगर और बी क्यू भी आ रहा है, सो हमें वो भी लिखना होगा ना. सो वी वुड राइट फर्स्ट हेयर बी के डैगर, बी एल डैगर, then we have a minus sign, and then order change L L K J, or we have L K K I capital. This is capital K, remember. This is capital K. Yeah. Uh, this we have B L dagger, B K dagger, and then n psi equals to 0. We can take out these scalar numbers because these are these overlaps represent some numbers. So we can, in fact, bring them out as common factors. So what we have left with, we are left with the summation over k, comma l, and then we have l k small and capital K I, l l and capital K J, and what is remaining is b K dagger, B L dagger minus, and obviously we would have a factor here of lambda because we have a change of basis. Lambda B L dagger, B K dagger, and then we have psi equals to 0. So this is basically the change of basis. So uh, in fact, we are writing two steps together. So the first step is the change of basis. Once we have changed the basis, then you want to check whether the order of creation of two particles is same. Yeah, it is same except for the factor which is lambda. Yeah, so that's why we have this factor. And so remember यहाँ पर मुझे यहाँ पर lambda लिखना चाहिए था initially, which I forgot. So इधर आएगा lambda. That's why we have this lambda here. Yeah. So there has to be a change of basis. Yeah. So and if there is a change of basis, then one needs to write the proper change of basis representation. So the lambda which was missing is because we forgot to write a lambda here. Yeah. So we write lambda here, and the lambda appears here, and the lambda appears here. So now we have this set of equations. So uh, if this is to give 0, yeah, that is on the right hand side we have 0 for any psi, for any initial state psi, then इसका मतलब ये हो गया कि each term on the right hand side must be 0 for any value of k and l. And this is basically when we say that if this equation above is 0, then on the right hand side, then this can only be 0 if each term on the right is equals to 0. Yeah. And this is the idea which is basically known as unitary symmetry. Yeah. And so using the idea of unitary symmetry, that is, so we say using the idea of unitary symmetry. यूनिटरी सिमेट्री का मतलब है कि if you can transform from one state to the new state, then you can transform from that new state to the old state. This is unitary transformation. And if this is true, then such a transformation is known as unitary symmetry. Yeah. मतलब i if this above equation uh, gives 0 for any initial state psi, uh, then each term on the left hand side must be 0, must be must be 0. And this is true for any value of small k and l. Yeah. And this is basically the concept of unitary transformation. That is, you can transform to a new state, and then you can transform from the old state to new state, and from the new state to old state. And this is basically would imply that this would imply then uh, B K dagger B L dagger minus lambda B L dagger B K dagger equals to 0. And with KL अगर मैं के एल को इंटरचेंज कर दूं विद के एंड एल interchanged, then we would have B L dagger, B K dagger माइनस, बिकॉज हमने कहा था ना किसी भी सीक्वेंस में कर लें बराबर होता है, द ओनली डिफरेंस इज दिस लैम्डा फैक्टर विच इज अ फेस फैक्टर. सो बी के डैगर बी एल डैगर equals to 0. Yeah. So in each case, the order doesn't matter, but the what matters is in fact a phase factor. Uh, और अगर मैं इनको कंबाइन कर दूं, दैट इज लेट्स से फ्रॉम दिस सेकेंड इक्वेशन, फ्रॉम दिस इक्वेशन, अगर मैं इसकी वैल्यू सब्स्टिट्यूट कर दूं यहाँ पर, तो मेरे पास क्या हो जाएगा, इफ यू सब्स्टिट्यूट दिस वैल्यू इन इन हेयर, तो हमारे पास क्या आ जाएगा देन, कंबाइनिंग the two equations, what we would get, b k dagger from the first equation, b l dagger minus lambda into lambda b k dagger b l dagger equals to 0, or you could write b k dagger b l dagger minus lambda square b k dagger b l dagger equals to 0. And from this we could say lambda square is equals to 1, and we have lambda is equals to plus minus 1, which is a very interesting and important result which is obtained from this change of basis. And then there are two basically solutions. One is plus and the other one minus. And these two solutions then will lead to two types of commutation relations. Yeah. So that is, there are two types of solutions. Lambda is equals to plus minus 1, leading to two types of commutation relation. Yes. And what are those for? So we could write for lambda is equals to plus 1. We would have a solution for AI dagger, AJ dagger minus AJ dagger, AI dagger. Yeah. And this is equals to 0. Or we could write AI dagger, comma AJ dagger. So this is in fact equals to 0. This is a commutation relation. And then for lambda is equals to minus 1 would imply AI dagger, AJ dagger plus AJ dagger, AI dagger equals to 0, which is AI dagger, comma AJ dagger. इसको हम यू लिखते हैं, रिप्रेजेंटेशन इसको यू करते हैं, और सब स्क्रिप्ट में प्लस साइन लगा देते हैं. ठीक है ना. equals to 0, and this is anti-commutation relation. And similarly for their adjoint as well. So this treatment is also valid for their adjoint, यानी for AI and AJ. या सो इसका मतलब हो गया कि ये हमारे पास दो एंटी कम्यूटेटर रिलेशंस आ गई और from your previous classes that lambda is equals to plus 1 corresponds to bosons and lambda is equals to minus 1 corresponds to fermions. So when we talk about creation of bosons, creation of two bosons, then we are using commutation relations. And when we talk about creation of two fermions, then we talk about anti-commutation relation. So we could write it. It is easy uh, to see that uh, lambda is equals to plus 1 corresponds to bosons and lambda is equals to minus 1 corresponds to fermions. Yeah, so this is quite easy. Uh, और इस चीज को कि y lambda is equals to plus 1 corresponds to boson and y lambda is equals to minus 1 corresponds to fermion, इसको हम इस तरह से समझ सकते हैं because AI dagger and AJ dagger acting on some initial state psi is same as AJ dagger and AI dagger combination acting on some initial state psi. These two sort of operator actions, two operator actions corresponding to creation of two particles on some initial state same. But with state I and J interchange, अगर हम उनको interchange करेंगे then equivalent to interchanging of two particles that would correspond to sort of an interchanging of two particles, and this would lead to either the interchange after interchanging it is basically symmetric, that is we have a plus 1 lambda is equals to plus 1 corresponding to a symmetric state, or if we interchange these two and we get a minus sign, then that would correspond to an antisymmetric state, and so that would be corresponding to fermions, जो कि हम इससे पहले इनिशियली बात कर चुके हैं, ठीक है ना. सो fermions and bosons की दो different representations we have already sorted out. So we can give the reason for this जो ये हमने लिखा है, this is because uh, AI dagger, AJ dagger acting on psi is the same as AJ dagger, AI dagger acting on psi, but the only difference, but with states I and J interchanged. States I and J. So I and J are two states, sort of, because a state with ith particle and a state with jth particle, and this is equivalent. equivalent to interchanging two particles. So this is as if we have interchanged two particles and leading to a plus one, to a plus one uh, in the wave function, in the wave function, which is symmetric under pair interchanges, pair interchange of boson, yeah, or alternately, we could say for fermions, uh, AI dagger and AJ dagger acting on psi is equals to minus AJ dagger, AI dagger acting on psi, because it is equals to interchanging two particles, which would lead to a minus sign with the wave function, and that corresponds to an antisymmetric state. Yeah. So because it is equivalent to interchanging interchanging two particles, leading to minus one, leading to minus one, or an antisymmetric state. Antisymmetric state. So that's why we have lambda is equals to plus 1 corresponds to a boson, and lambda is equals to minus 1 corresponds to a fermion. Corresponding to plus 1 and minus 1, then we would have two commutation relations. We have two types of commutation relations. One is the commutation relation and the other one is anti-commutation relation. Remember from your course uh, in third year honors, which is quantum mechanics 1, the recipe for quantization of classical particles is to first identify the dynamical variables. The next step, you promote those dynamical variables to operators. And the third step, all those dynamical variables have some constraint or restriction attached to them. And that constraint or restriction is basically in classical mechanics that is known as the Poisson bracket, but in quantum mechanics it is known as commutation relation. And so when you talk about particles of type having spin equals to 0, 1, and that is integer spin, which you call them as boson, then for those type of particles, the constraint or restriction which you impose on those dynamical variables is known as a commutation relation. And for those type of particles for which the spin is half integer multiple, that is fermions, then for those type of particles, the restriction one imposes on those dynamical variable is not commutation relation but anti-commutation relation. And you can see mathematically, you can see the difference of a plus sign and a minus sign in those relations. And corresponding to that, you have this lambda, which is equals to plus 1 and lambda is equals to minus 1. So this is basically the reason हम ये लेते हैं. And this is very important. In fact, पार्टिकल फिजिक्स के हवाले से एंड क्वांटम फील्ड थ्योरी के हवाले से when you write equations of motion for such particles, then there are basically two different types of equations of motions. One corresponding to bosons and the other corresponding to fermions, which is basically Klein-Gordon equation for bosons and Fermi-Dirac or a Dirac equation for fermions, yeah, which is whose mathematical treatment is different for both these particles. Uh, we should also emphasize that AI dagger जो है that creates a particle, एक particle in a state uh, and having correct symmetry, symmetric or antisymmetric. That is either symmetric for bosons or antisymmetric for fermions. This is important to remember. Uh, so let's write this in terms of note. What is the note here? Uh, it is important that AI dagger creates a particle, ठीक है, in state I with the correct symmetry. So this is basically symmetrization postulate हमने याद होगा ऊपर किया था कल last time. And so this is nature. That is nature has two types of particles, and for those two types of particles, when you describe their evolution, their equation of motion, or their state, the nature dictates that there is one type of wave function which is symmetric and another type of wave function which is antisymmetric. So there is nothing from mathematics which basically proves it is basically a postulate of nature. Yeah. So either symmetric for bosons and antisymmetric antisymmetric for fermion. Yeah, so this is basically something which is very important. And from this same argument जो अभी हम ऊपर लिख रहे हैं, इसी की मदद से we can also prove Pauli exclusion principle. So in similarly, when I is equals to j, that is the state is same. Yeah. So lambda is equals to plus 1. Yeah, so lambda is equals to plus 1 relation, which says that dagger AI dagger दोनों I is equals to j कर दिया ना, is equals to किसके बराबर है, AI dagger and AI dagger. So lambda की हमने वैल्यू 1 ले ली, दोनों बराबर है. Whereas